Hello, and welcome to our talk today. This is a talk by me. My name is Ali, and Shasha, my partner here. We are from LinkedIn, where our mission is to create an equal opportunity for every member of the global workspace. Essentially, that's all of you. And in this mission, we are driven by AI, and today we're going to present how inference graphs are being used at LinkedIn. Yeah, Shasha, you want to introduce yourself quickly?
My name is Sasha. We work on AI platform at LinkedIn. Welcome to our talk.
All right, so we're going to walk through this agenda today. We're going to talk about some of the challenges that we see that we want to solve for, how Reserve is helping us achieve and solve those problems. We're also going to be talking about as we build on top of Reserve, where we see that we can contribute to a growing Ray and the Ray ecosystem. And then we're going to be just highlighting some solutions and success stories. Just to start off, this is our inference stack. Very standard inference stack you would probably find anywhere. If you go to any company, you'll probably find this. You basically have a serving system, a serving service which is capable of serving in models. It has a bunch of feature. It gets a request, inference request. Does a bunch of feature producing, hands it over to inference server like Triton and TensorFlow serving is what we use as a backend, and the inference is done on that stack. So the middleware service is really doing feature massaging and feature fetching and then handing it over to inference server. We do have multi-tenancies. We have many users. Our multi-tenancy story today is literally making a copy of a stateless sort of a service. So each pod or each instance of the service is replicated n number of times for multiple tenants. We do have various use cases running on top of these. There are LLM use cases that run in this configuration, but there are also personalization models, which are also a significant part of our infrastructure, which are on top of this infrastructure. We also have a lot of experimentation and ensemble inference use cases where we want to do A/B testing and various other type of experimentation on top of the infrastructure that we provide. And this story is pretty straightforward, which is, again, create multiple tenants of one experiment type and then another experiment type and, manage this army of multi-tenants, even the experimentation universe. And then the client system switches between these tenants depending on the experiment configuration. On the ensemble side, we have a similar story where, we host various type of models in their own tenants and then switch between them on the client side, which means that if you want to do model 1 and then do some business logic and then do model 2, you would make round trips to the inference stack. Our inference ecosystem is made up of online, nearline, and offline use cases, and these are very important for us. There are a lot of, in addition to just pure online use cases, the nearline use cases add a lot of value to LinkedIn in terms of computing embeddings and features that are then used for various other use cases. Same thing with offline. Offline has two applications you can think of. One is to validate your model. So once you've trained a model, you want to validate it and see if it is behaving the way you expect it to behave. So that's one use case of offline inference. The other use case of offline inference is actually generating, running a large compute on data and then generating embeddings for that. Some of the limitations that we see in our current stack is basically, obviously this ML space is constantly changing, and having a custom stack adds friction in that path to adopt to new changes. So we want to build something that is more fluid and we can adopt faster to upcoming trends. We do have this homogeneous versus heterogeneous. We are moving to a world where GPUs become very important, and there are different type of GPUs that come into play, and we want to build an infrastructure that can play over a heterogeneous infrastructure and not just have like homogeneous multi-tenants replicated a number of times. We want to solve for autoscaling. We want to have better resource utilization. And then, we want a story where you could move from your offline inference world to an online inference seamlessly. So today, if I just scroll back a slide, if you have to move from your offline inference stack to an online inference stack, it's a significant uplift. You have to rewrite a lot of your code to work in the online stack and differently because it works very differently in the offline stack. And this is where we started experimenting with Rayserve and started to play around an idea on how Rayserve can help us solve these problems. So basically we want to simplify this management of this complex architecture, heterogeneous architecture. We want to have better integration with open source so that we can get new and upcoming things faster into the stack. And we're also looking for cross-language interoperability because a lot of LinkedIn infrastructure is built on top of Java, whereas the new and upcoming things in the machine learning world are mostly happening on the Python side. So we want to have this ability to interoperate between these languages. So what we have designed is this Rayserve-based inference runtime. And essentially what you can see here is a heterogeneous infrastructure where each graph or each inference graph is deployed as an independent unit. You can replicate them differently. For example, if you're running A/B experiments and you want your control to be scaled out at 50% and your other experiments scaled out at different other percentages, you could deploy all of that in a single infrastructure and scale them up and down at will. We are integrating this with our experimentation framework so that you can do seamless and without any significant issues rollout on production. So this graph basically shows you that nodes are split across multiple different inference graphs. And then each inference graph is also split into multiple nodes, and these nodes could be different based on whether you are running a CPU compute or a GPU compute. This helps us isolate workloads that are data intensive, let's say on CPU, but and run only the inference on GPUs, which helps in better utilization. We obviously have integrated all of this with our load balancing and rest of the stack. We have also ported the same design over to our offline inference runtime. So basically, you can take the same inference graph that you would define in an online world and run it in offline, or you could take it an offline graph that you define it offline, and then you can run it online. And it works exactly the same way. The only difference is that you are deploying one in the Rayserve and the other in Raycore. Some of the challenges that we see that we are trying to figure out how to solve is basically adopting Ray at LinkedIn ecosystem LinkedIn is done in a very special way, so we're adopting Ray into that, TLS, configs, how do you run Java and Python together, logging, crash reporting, all of that into the LinkedIn infrastructure. Code rollout and fault tolerance is another thing that we're looking at very significantly. Autoscaling and dynamic actor pooling is another thing that we're looking at. So basically, we want to see if we can build actor pooling in a way that it can be shared across multiple deployments, and you could have like more advanced routing between them. We're also looking for in-place graph updates, and rate limiting is another thing that we're looking at. With that, I will hand it over to my partner Sasha here, who will talk about the rest of the concept of an inference graph.
Hi. Again, my name is Sasha. I should say it feels really amazing to participate in face-to-face event. I think it's my first in like 4 years. It's great to have interaction. We are AI platform at LinkedIn, and our users are AI engineers who train models and create those workflows based on models. So you might be wondering during the talk, like, what is inference graph? So we want to get a little bit into that. So this is, what you see here is the simplest inference graph. Basically, just inputs that are fed to a model, and then outputs are sent back to the users. That's the simplest possible thing. Now, one other example is for when you need to like pre-process some data and do some post-processing. For example, for image processing, right? So you would want to do some scaling, I don't know, color management, or some quantization. So that would be pre-processing. So then you do inference, then you do post-processing. That would be output. So that's another example of inference graph. And then yet another example with features where before even calling the model, you just go into feature store, retrieve the feature data, and hand those features to the model. And then after you did inference, you want to record what features were there for this particular inference. And maybe you're doing log and wait or for debugging, you need this information. So this is yet another way of doing this. And last example in this series, multiple models. It's like ensemble models. Multiple models using the same feature fetching process to kind of save time, and then blending the model results. So these are all examples of things that we want to do beyond our users want to do beyond simple model inference, right? And we need something to do that. And as Ali talked about, we use Array Framework for that. And he went into a lot of like low-level detail of how this is happening. But our goal is to make not only the global workforce, but our AI engineers productive. And for that, we want them to work at a higher level and without like getting into low-level details of how it is implemented. So that's why we created a platform or framework that we call Proxima. That's an internal name. This is a platform for high-level authoring of inference graphs. So basically, it allows them to independently author and deploy and run the whole process, monitor and everything of this inference graphs. So the graphs I showed you, it's still simple. Like in real world examples, they will be much more complicated than that. So of course, we want this to be duly integrated with all the development ecosystem, use the CI/CD pipelines and experimentation systems and feature infrastructure and all the pieces of the infrastructure that we need to make it work. We need to scale on CPUs and GPUs. And GPUs, as we will know, are really hard to get and expensive. So we want to utilize them to its full power. And we need a lot of technical understanding how to do that. Again, that's for platform to handle, and kind of unique, or maybe not unique, but special situation for LinkedIn is that a lot of services and infra is written in Java language, and a lot of ML is written in Python and native, like C++, and we need an easy way to integrate those parts, and Array is very helpful with that. So this is the problems how we were trying to solve. So this is just an idea of how this whole stack looks like. There's a Kubernetes at the bottom, and there's a control plane, something like parallel to, I would say, KubeRay, but it is specific for kind of LinkedIn applications and microservice architectures and things like that. So that's our custom control plane. And we run a reserve on top of this control plane. And then we run our like a framework runtime, inference DAG runtime on top of that, and deploy using our deployment platform. So in order to configure those DAGs, we chose to use Python, which we feel is intuitive for AI engineers. And then it is integrated into CI/CD process, and that allows AI engineers to do their work independently and don't depend on like production application engineers to deploy their work or their models or their graph. So basically, everybody does their own like things, and everybody's on call. Right? And then obviously operability tools, profiling, monitoring, configuration, it is all taken care of by the platform. So this is an example of what do we mean by intuitive Python API for the graph. So this is the graph that we already talked about. And this is basically how this graph will be written in our Python API. You can see that you just create a bunch of objects which represent models that needs to be run inference. And then you combine features of those models so that you can run the feature fetch operation once to save time. And then you run, so this, I don't have a pointer here, but in the last line, near M1, you see like in the brackets, that's the inference of the first model, and then M2 with the brackets is the inference of the second model, and then these models are blended with the weights. So that's basically looks like Python. It is basically, it implements some very limited subset of Python. And I'll talk a little bit why, right? So there's a process that this whole system kind of goes through. So AI engineer authors their graph in this myservice.py. And then there's a build process that builds two things. It builds this deployment artifact. So basically that it takes this graph definition from Python and converts it to some like high-level definition or internal representation, writes it as a protobuf file, and that file could be loaded in a different system. Why do we need to convert Python into something? Because we have Java runtime that wants to load this and execute this, and Java cannot execute Python. Or it could be Python runtime. So that's one thing we're creating during the build. The other part is kind of straightforward. It is like gRPC proto file that represents the service. So if it is this function definition, this function signature that takes these two inputs, there will be equivalent proto definition for that signature that is just created, and then we go through the normal gRPC process of compiling this into stubs in any chosen language, and application engineers can call our service using those stubs. So that's the process how this system works. So here's our status. It's under active development for a few months. But we already have production use cases, and we'll talk about it a little bit. And one of the questions to the community is how much interest how interesting is this whole thing that allows you to express the graphs and run them, deploy them, and run them, and whether we should be trying to publish this code as an open source. So that's kind of open question for us, so we'll appreciate any feedback on that. This is one of the examples of production use cases that we run with this stack. This application that allows recruiters basically become more productive, save time, and improve the engagement with their user or with people they communicate with, using AI models that are running on the stack on the Ray. Basically, that's all we wanted to talk about. Any questions?
Go ahead.
I have a question. So you talked about pre-processing steps. Are you able to define that in Python as part of like that inference graph? And how do you handle like serialization of like your Python code and stuff like that?
Okay.
Can you repeat the question one more time? Sorry.
I guess first part of the question is like, do you support Python pre-processing steps in the inference graph? And then how do you like handle the sort of code assets?
So let me
So I'll just repeat the question.
Yeah.
The question is, do we support pre-processing steps in the inference graph and in the API that we just showed? And how do we handle serialization, deserialization for that? You want to answer the question?
Sure. So pre-processing, post-processing steps, all of that is supported via what we call Proxima operators. So basically, these are functions that are built into the system. And in the graph, in the graph definition that I showed you, it looks like just Python call to a function, right? But behind the scenes, it's a little bit more involved than a function, but not much. And you can have those operators for any types of function, including pre-processing. Pre-processing, like for images, for example, there's a bunch of like more or less standard methods, right? So I think it could be covered with a limited number of operators, and that can be done this way.
But add to what Sasha said is basically we support two types of use cases. One is these generalized pre-processing. Sasha, you mentioned image-based processing, which can be generalized. We can have a library already integrated into the runtime, and therefore you don't have to really code. You just have to point to us saying, this is what I want to use, right? So that's one use case. The other use case is like more specialized, where you want to do some really low-level processing, which is only specific to your use case. We support that as well, where you can contribute sort of your own operator, and that can only be run for you in there. So there's an inference graph, which is like a pointer to functions, and then there is this operator code, which is the code that houses the logic for running the pre-processing, post-processing. How do we handle serialization, deserialization? That's a very good question. That's one of the things that we are trying to figure out, how to juice out Ray's primitives. So we to start with, we are using obviously object store. So we just store Ray, use Ray object store to store and get the value. Now the money basically is in the place of like co-locating these things so that the object store copy over the network can be saved and all those things. So we're working on how we can co-locate operators and how we can co-locate the graph, parts of the graph, so that we can save serialization cost. But there are cases where you will have to pay the serialization cost, and we will have to work on like figuring out the fastest way to get things out.
Yeah, there was somebody behind. Oh.
Yeah, go ahead.
For the online case, were you able to get the same QPS and the same latency that you had before Ray, after you moved to Ray? Because you had a very specialized solution, custom built, and you turned it into a general solution might not be very specialized like that.
Yeah, I'll just repeat the question. So I think the question is that when we've moved to using Ray, did it help us in speeding up or slowing down, whichever it is, right? Basically the overhead of the platform. What is the additional overhead? Is that what you're asking for?
Yeah, so what's the additional overhead, and were you able to match your previous QPS?
Match your previous QPS.
And the latency of each request for the online case?
Yes. So the second part of the question is, were we able to match our latency requirements and in the old system versus the new system, especially, right? So there are two use cases here. One is the LLM use case. We started building the LLM use case on top of new infrastructure. So we really don't have a baseline there, but the baseline that we're trying to measure against is that overhead of the platform, right? So most of your LLM time is spent inside the GPU doing the inference. So we want to like figure out what is that additional overhead that Ray is, or the stack that we have built on top of Ray is creating. And we don't have those numbers here, but that is minimalistic right now. Like it's in milliseconds, so it's like really tiny amount of overhead compared to the LLM use case. Now, the other use case that we have, which is the personalization models, which are different than LLMs, right? So in the personalization models, latency is super important, and the model, the overhead from the model itself is not that much. In that space, yes, we are removing some of the layers that we've created for the LLM hosting to run the LPM or the personalization models more intricately, so that we don't pay the cost of serialization, deserialization. I think that's where the cost really is, to juice out the SERDE cost.
Yeah. So it's most likely it'll go into Java runtime.
Go ahead.
That percentage.
Yeah, go ahead. Yes.
Yeah. I want to follow up on that one. On the latency side, have you compared the latency on inference on Ray versus LLM API? And is there a significant difference? And then I have another question. Everybody's talking about cost.
Yeah.
Do you have a general idea about the cost with this?
Got it. So repeating the question, I think you're asking about what's the first part of your question again? Latency for what?
Latency between
Ray and API.
Yeah. So the latency difference between this infrastructure for LLM and AI, again, I think I'll just repeat what I just said before. Is it is really about saving the cost of SERDE, the network trips and stuff like that, which will really impact your performance, right? So as long as you can minimize that, that is where the game is. And we are like our new stack, like the way we are using Ray offers you primitives around affinity-based placements and various other ways to minimize the cost of transmitting data over the network for a long period of time. You can localize actors, and you can use object store that way to minimize the cost, right? So those are the primitives that we are looking at. The actual cost of, as I said, the LLM hosting at least, right? The cost that we have seen is minimal from the overhead that we have seen so far. I think there's more color to this question because it gets complex when you have like an ensemble models with multiple models running one after the other, or we have large amount of pre-processing, post-processing running before and after the model inference, and then I think the measurements will be different. But for the vanilla use cases, we don't see a lot of overhead from the framework. Yes. Yes. So the question is that for large models, the millisecond overhead is probably not that significant, but for models that care about performance a lot, millisecond differences would matter a lot, or millisecond overhead would matter a lot. That is absolutely right, and that's why we have like two different stacks. If you saw, a lot of that is coming from Python because SERDE in Python is costly. And we are looking at different solutions. One of the things that we already have in the works is a Java-based runtime on top of Ray, which is no Python in the call path. It is all Java in, Java out. Like it's just working on top of Java. We are also trying to see if we can invest in native C++ based actors and all that to reduce the overhead of SERDE. From that point of view. So that's our play there. We haven't solved all the problems yet, but we have seen the difference between Java and Python definitely as a significant cost saving that happens. And also, like just to add here that most of LinkedIn stack is in Java. So any overhead, like for example, feature fetching is a sort of an overhead for us because if we do inference in Python, but feature fetching in Java, then it becomes automatically very costly. So we are investing in Java side a lot to basically reduce that cost as well. Yeah, go ahead.
You said you're using the inference graph for both online and offline.
Yeah.
Inference. So how do you schedule offline inference if you have like a huge data set?
Yeah. So the question is, how are we scheduling offline? Because we are using the same graph for online and offline, so how are we scheduling offline? That's the question. And the answer to the question is basically what we do is, on the offline world, we use array data sets to scale out the workload. What you are deploying is an actor pool, basically. And in the online world, you are deploying a serve deployment, which is an equivalent of the actor pool in the online world. So you scale out based on the actor pool strategy. So scaling out configurations are different for online and offline, but the inference graph remains exactly the same. So the user experience, if you think about the user experiences, literally they go and write the inference graph once, and then they're able to, just because of our framework, they're able to run it both in online and offline. Go ahead.
Last question.
Go ahead.
Regarding the survey cost, is it due to just the fundamental differences between compiled languages and dynamic languages, Python, Java, or is it due to global interpreter lock in Python or is running on single threading?
I think it's more to do with just how the languages work. I'm pretty sure the global interpreter GIL also plays a role there. We haven't really measured removing GIL, what is the cost saving. We haven't measured that, if you were asking that question. But I think even if you remove that, the overhead is still going to be still significant.
Yes, serialization in Python is, it goes through, does a lot in Python, and does a lot of like lookups and field lookups and all that. And that could be very costly.